Hello everyone, and welcome to today's video lecture, which is on the Bernoulli numbers, cotangent and tangent. Now, I've said before that the Bernoulli numbers are these amazing numbers that show up in all kinds of mathematical contexts. And one of the most widely known contexts, which we'll explore today, is their connection to the Taylor series expansions for the cotangent and tangent functions. So my goal for today's video is pretty straightforward. It's just to show how the cotangent and tangent functions can be written as Taylor series involving the Bernoulli numbers. Now, we've seen Bernoulli numbers arising in the context of Taylor series already. In fact, I'm going to ask you to recall a couple facts. The first of which is that the Bernoulli numbers are a sequence of rational numbers that appear as the coefficients in the Taylor series for something known as the exponential generating function. And the exponential generating function for the Bernoulli numbers is this function, x over e to the x minus 1. And it can be expanded as a Taylor series whose coefficients are the Bernoulli numbers. So this equals b sub 0, the 0th Bernoulli number, times x to the 0 over 0 factorial, plus b sub 1 times x to the first power over 1 factorial, plus b sub 2 times x squared over 2 factorial, plus ... and so on. And this series can be written more concisely as the sum, indexed from k equals 0 to infinity, of the kth Bernoulli number b sub k times x to the k over k factorial, where, concretely speaking, the first few Bernoulli numbers are b sub 0 equals 1, b sub 1 equals negative a half, b sub 2 equals 1 over 6, b sub 3 equals 0, b sub 4 equals negative 1 over 30, b sub 5 again equals 0, b sub 6 equals 1 over 42, and so on. Now, if any of that material is unfamiliar to you, I would encourage you to check out my video on the exponential generating function for the Bernoulli numbers on my YouTube channel. But moving ahead, I'm going to also ask you to recall a couple more facts. First of which is that the cosine function, cosine of x, can be written in terms of the complex exponential, and the formula for that is cosine of x equals e to the ix plus e to the negative ix all over 2. The sine function can also be written in terms of the complex exponential, and the formula for that is sine of x equals e to the ix minus e to the negative ix all over 2I. If these identities are new to you, I would refer you to my YouTube video on my channel on the complex sine and cosine, where I derive them. Now, given these identities, for cosine of x and sine of x, we can derive a new identity for the cotangent function, because remember, the cotangent of x just equals cosine of x divided by sine of x. So when we divide cosine of x by sine of x, we find that cotangent of x equals e to the ix plus e to the negative ix all over 2, and then all of that is divided by e to the ix minus e to the negative ix over 2I. Simplifying this expression, we would have that cotangent of x equals e to the ix plus e to the negative ix over 2, multiplied by 2I over e to the ix minus e to the negative ix. When we multiply these things together, the 2's cancel, and then I'm just going to bring that I in the numerator out in front to get cotangent of x equals I times the quantity e to the ix plus e to the negative ix all over e to the ix minus e to the negative ix. So I'll move that expression to the top here, and now I just want to simplify this expression a little bit more by multiplying by what a former math teacher of mine called a creative form of 1. So I'm going to multiply this expression by e to the ix over e to the ix. So when we multiply through, we get that cotangent of x equals I times the quantity, well, e to the ix times e to the ix is e to the 2ix, and then e to the negative ix times e to the ix is just e to the 0, which equals 1. So in my numerator, I have e to the 2ix plus 1. And then in the denominator, when I do the multiplication, I get e to the 2ix minus 1. So cotangent of x equals I times e to the 2ix plus 1 all over e to the 2ix minus 1. Well, when Leonhard Euler was messing around with this stuff, a light bulb went off in his head. And maybe for some of you a light bulb is going off as well. Because you'll remember that the exponential generating function for the Bernoulli numbers is the function f of x equals x over e to the x minus 1. And here we have a representation of the cotangent function, where the denominator of that function is e to the 2ix minus 1. Well, that's not exactly the same expression, but it's pretty close. So it should strike us that hidden within this expression for the cotangent function is the exponential generating function for the Bernoulli numbers. So we want to perform some manipulations on this function to bring that out. Specifically, we want to produce a expression of the form 2ix over e to the 2ix minus 1, which would be completely parallel to the exponential generating function for the Bernoulli numbers, which again is x over e to the x minus 1. And here's the manipulation that will bring that about. I'm going to rewrite the numerator of this expression for cotangent of x as e to the 2ix plus 2 minus 1. That's the exact same quantity as e to the 2ix plus 1. I've just written a plus 2 and then a minus 1 there. But look what happens when we do that. We then have that cotangent of x equals I times the quantity, and now I can split the fraction up, 2 over e to the 2ix minus 1 plus e to the 2ix minus 1 over e to the 2ix minus 1. Well, that second term just cancels out to being 1. So now I have cotangent of x equals I times the quantity 2 over e to the 2ix minus 1 plus 1. Now I can multiply through by I, and I get that this equals 2I over e to the 2ix minus 1 plus I. Now we're getting very close to our goal. All I have to do is multiply that first term there by a creative form of 1. I'll multiply it by x over x, and I get that cotangent of x, bringing in that x into the numerator there, equals 1 over x times 2ix over e to the 2ix minus 1 plus I. Just for cosmetic reasons, let me rearrange the order of these terms. So we'll have cotangent of x equals I plus 1 over x times 2ix over e to the 2ix minus 1. So we've revealed that hidden within our original version of the function cotangent of x is an expression that's equivalent to the exponential generating function for the Bernoulli numbers, where 2ix is taking the place of x. So now we're able to write out our Taylor series for cotangent of x, making use of the Bernoulli numbers, and we have that cotangent of x equals I plus 1 over x times the series b sub 0 times 2ix quantity to the 0 over 0 factorial plus b sub 1 times 2ix quantity to the first power over 1 factorial plus b sub 2 times 2ix quantity squared over 2 factorial plus, and I'll just write out the formula for the other terms in the series, the sum indexed from k equals 3 to infinity, since we already covered the k equals 0, 1, and 2 cases. So indexed from k equals 3 to infinity of b sub k times the quantity 2ix to the kth power over k factorial. So now to simplify this expression, I'll just plug in our values for b sub 0. b sub 0 equals 1, and I'll plug in the value for b sub 1 that equals negative 1/2. And then I'll just pull the b sub 2 term into my indexed sum. So I'll start the index there at k equals 2. So 1 times 1 over 1 just equals 1, and negative 1/2 times 2ix just equals negative ix. And now I'm going to multiply through by 1 over x. So when I do that, I have cotangent of x equals I plus 1 over x times 1 plus 1 over x times minus ix plus 1 over x times this sum. So I get I plus 1 over x minus I plus 1 over x times the sum from k equals 2 to infinity of b sub k times the quantity 2ix to the kth power over k factorial. Now the i's cancel, and I get cotangent of x equals 1 over x plus 1 over x times this indexed sum. Now let me bring that expression to the top line there. Now, with the exception of b sub 1 equaling negative 1/2, all the odd indexed Bernoulli numbers, b sub 3, b sub 5, b sub 7, b sub 9, and so on, all those odd indexed Bernoulli numbers actually equal 0. So we can write this more concisely still as cotangent of x equals 1 over x plus 1 over x times the sum indexed now from k equals 1 to infinity of b sub 2k times the quantity 2ix to the 2kth power over 2k factorial. I want to focus on that leading term there, 1 over x, that's outside of the indexed sum. Now, as it happens, b sub 0, the 0th Bernoulli number, equals 1. So it won't do any harm to write that cotangent of x equals that term 1 over x times b sub 0, since b sub 0, again, is just 1, times the quantity 2ix to the 0 over 0 factorial. 2ix to the 0, of course, is just 1, and 0 factorial is just 1. So I can actually rewrite this entire expression as cotangent of x equals 1 over x times b sub 0 times 2ix quantity to the 0 over 0 factorial plus the indexed sum from k equals 1 to infinity. Now, why was it such a great idea to rewrite that leading term 1 over x in that way? Because when we do that, we see that the term b sub 0 times 2ix to the 0 over 0 factorial is in the exact same form as all the terms within the indexed sum. So in fact, they can be combined into one sum where I just start the indexing at k equals 0 instead of k equals 1. So when I do that, I get cotangent of x equals 1 over x times the sum, indexed now from k equals 0 to infinity, of b sub 2k times the quantity 2ix to the 2k over the quantity 2k factorial. So let me bring that again to the top, and we can simplify this even further, because it turns out that I to the 2k, that just equals the quantity I squared to the power of k. In other words, that just equals negative 1 to the k. So I can rewrite this expression as cotangent of x equals 1 over x times this index sum, k equals 0 to infinity, of b sub 2k times negative 1 to the k times 2x to the 2k all over 2k factorial. And now we have to just make one final simplification, bringing that 1 over x term into the sum. We get that cotangent of x equals the sum from k equals 0 to infinity of b sub 2k times negative 1 to the k times 2 to the 2k times x to the 2k minus 1. Multiplying through that 1 over x just reduces its exponent by 1, so it's x to the 2k minus 1, all over 2k factorial. So there you have it, this very beautiful and concise formula for the Taylor series for cotangent of x in terms of the Bernoulli numbers. And just to give you all a sense of what this expression looks like, let's just work out the first few terms of cotangent of x. So we'll have that cotangent of x equals, first letting k equals 0, b sub 0 times negative 1 to the 0 times 2 to the 0 times x to the negative 1 all over 0 factorial. Plus, letting k equal 1, b sub 2 times negative 1 to the 1 times 2 to the second power times x to the first power all over 2 factorial. Plus, letting k equal 2 now, b sub 4 times negative 1 to the second power times 2 to the fourth times x to the third power all over 4 factorial. Plus, letting k equal 3, b sub 6 times negative 1 to the third power times 2 to the sixth times x to the fifth power all over 6 factorial. And we'll just do one more term, letting k equal 4 now, plus b sub 8 times negative 1 to the fourth times 2 to the eighth times x to the seventh power all over 8 factorial, plus dot dot dot. Now I'm going to substitute in the actual values for the Bernoulli numbers, and we get this. And now I'm going to take care of the negative 1 terms. Negative 1 to an odd power is negative 1, while negative 1 to an even power is just positive 1. And now I'm just going to write out the terms that are the even powers of 2. And now I'm going to multiply out the factorials in the denominator there. And then I'll multiply all of the terms in the denominator. So we'll multiply 6 by 2, and 30 by 24, and 42 by 720, and 30 by 40,320. And when you reduce those fractions finally, you get the first few terms for cotangent of x. You get the cotangent of x equals 1 over x minus 1 over 3 times x to the first, minus 1 over 45 times x cubed, minus 2 times x to the fifth over 945, minus x to the seventh over 4,725, minus dot dot dot. So we just saw that the Taylor series for the cotangent function can be written in terms of the Bernoulli numbers, and it turns out that the Taylor series for the tangent function can also be written in terms of Bernoulli numbers. But to do so, to derive that relationship, we need the following identity. Cotangent of x minus tangent of x equals 2 times cotangent of 2x. So here's a brief and to the point proof of that identity. Cotangent of x minus tangent of x equals cosine of x over sine of x minus sine of x over cosine of x. Now we want to get a common denominator here, so I'll multiply cosine over sine by cosine of x over cosine of x, and I'll multiply sine x over cosine x by sine x over sine x. And now with that common denominator, we have that this equals cosine squared x minus sine squared x all over sine x cosine x. Well, even if this identity that we're proving isn't familiar to you, I hope that you will at least recall from high school trigonometry your double angle identities. Cosine squared x minus sine squared x equals cosine 2x. So we have cosine 2x over sine x cosine x. And now I'll multiply this by a creative form of 1. I'll multiply this by 2 over 2. So we get that this equals 2 cosine 2x over 2 times sine x cosine x. But that 2 sine x cosine x in the denominator, that's just equal to, double angle formulas again, sine 2x. And of course, cosine 2x over sine 2x is just cotangent 2x. So we've proved the identity. Cotangent of x minus tangent of x equals 2 times cotangent of 2x. QED. Well, why do we need this identity? Because we can rearrange it to write tangent of x purely in terms of cotangent of x and cotangent of 2x. So when I rearrange the identity, I get that tangent of x equals cotangent of x minus 2 times cotangent of 2x. But we already found the Taylor series for cotangent of x, so we can use it now to derive the Taylor series for tangent of x. So by the Taylor series for cotangent of x, we would then have that tangent of x equals the sum indexed from k equals 0 to infinity of b sub 2k times negative 1 to the k times 2 to the 2k times x to the 2k minus 1 all over 2k factorial minus 2 times, and here's the Taylor series now for cotangent of 2x. We're just going to plug 2x in place of x. So minus 2 times the sum from k equals 0 to infinity of b sub 2k times negative 1 to the k times 2 to the 2k times 2x, quantity to the 2k minus 1, all over 2k factorial. And now, in the next line, I'm not going to do anything to that first sum. For the second sum, I'm just going to expand out that 2x quantity to the 2k minus 1, so I'll get that this is b sub 2k times negative 1 to the k times 2 to the 2k times 2 to the 2k minus 1 times x to the 2k minus 1 all over 2k factorial. And now let me bring that to the top line there. I'm not going to do anything to the first sum, and now I'm just going to take that leading coefficient 2 in front of the second sum and pull it into the sum, so I'll have it multiply that term 2 to the 2k minus 1, so that term will just become another 2 to the 2k. Now, so far, we've been writing this equation as two separate summations, one being subtracted from the other, but if we look, we see that they both have the same index. So I can bring this whole expression together as one sum and just subtract the terms within it. Now, if you look at the numerator of my second term there, I have two factors of 2 to the 2k, so I'm just going to pull one of them out in front here. And why have I done that? Because it shows then that these two terms are actually identical to each other, except that the second one is being multiplied by a factor of 2 to the 2k. So we can go ahead and factor this. And when we do, we find that tangent of x equals the sum index from k equals 0 to infinity of b sub 2k times negative 1 to the k times 2 to the 2k times x to the 2k minus 1 all over 2k factorial times the quantity 1 minus 2 to the 2k. So I'll just bring that to the top line there. Now, when we look at this sum, when k equals 0, the term 1 minus 2 to the 2k, that just equals 1 minus 2 to the 0, which equals 1 minus 1, which equals 0. So we might as well start our summation indexed from k equals 1 to infinity instead of from k equals 0 to infinity, because the k equals 0 term just equals 0. Another cosmetic change I'd like to make to this sum, that 1 minus 2 to the 2k factor, that's going to be a negative number. So let's just factor out a negative 1 and switch the order of those terms. So that factor will then become 2 to the 2k minus 1 times negative 1. So our Taylor series for tan x is now the sum from k equals 1 to infinity of b sub 2k times negative 1 to the k times negative 1 times 2 to the 2k times 2 to the 2k minus 1 times x to the 2k minus 1 all over 2k factorial. Now, negative 1 can also just be written as negative 1 to the power of negative 1, and if I do that, I can combine its exponent with the negative 1 to the k. So my sum will then be, from k equals 1 to infinity, b sub 2k times negative 1 to the k minus 1 times 2 to the 2k times 2 to the 2k minus 1, close parenthesis, times x to the 2k minus 1 all over 2k factorial. And that is the final form for the Taylor series for tangent of x. Now, just as we did for cotangent of x, I want to at least exhibit the first few terms of tangent of x. I'm not going to perform all of the calculations for this because you can follow the example from cotangent of x to do this, but just so that you can see what it looks like, the first few terms of tangent of x are tangent of x equals x plus x cubed over 3 plus 2 times x to the 5th over 15 plus 17 times x to the 7th over 315 plus ... So there you have it. We've derived Taylor series for cotangent of x and tangent of x in terms of the Bernoulli numbers, which is a pretty unexpected, I think, and awesome result. Well, thank you so much for watching this video, and if you enjoyed it, please like or subscribe to my channel. Thanks again.